Hello, my name is Andrew and I'm from the University of Adelaide. In this piece of work, me and my colleagues present to you one of the first physical world attacks on aerial imagery, more specifically against a car detector. What we did was optimize, fabricate and install adversarial patches on or near cars to hide them from being detected by an object detector. We want to show that physical world attacks are a realistic threat on aerial imagery detection, but more importantly, pave way to design of new defense methods against these attacks. I'm going to start off by defining the attacker in terms of his or her goals, knowledge, capabilities, and strategy. The goal of the attack is to generate adversarial patches that can prevent cars from being detected in two scenes of attack, side street and car park. As seen on the right, the patches are to be placed on the roof of cars or often around cars. And lastly, the patches should be robust to different environmental conditions. The attacker is assumed to know everything about the detector, such as its parameter values, architecture, loss function, optimizer, etc. The attacker can optimize and evaluate patches in the digital domain and perform a physical world attack by printing them off and placing them in the scene of attack. The attacker will create patches by solving a minimization problem, which I'll explain in more details in later slides. Before we can generate a patch and thus perform a physical world attack, we need to train a detector that can detect cars in aerial images. We do this by training a YOLO v3 object detector on the car's overhead with context dataset, or CALC in short. Below are some images from this dataset. Next, we're capturing collected data from two scenes that we want to hide cars from being detected in. Cars in the side street scene and cars in the car park scene. Now we're ready to create a patch. As you can see, the patch optimization process begins with a patch that goes into a transformation block. The purpose of this block is to simulate placement and printing size uncertainty of the patch when placed in the scene, the lack of color fidelity of the printing device, and the different lighting conditions in the field. Geometric transformations include scaling and rotation, and color space transformations include brightness and contrast adjustment and random noise. Next, the patch is embedded into a training image. Since the patches are situated outdoors, we also apply weather and seasonal effects to that training image. Then the training image is passed through the car detector. Lastly, the loss is calculated, and as you can see, it comprises of three terms, where the first term extracts the maximum objective score predicted by the car detector. Minimizing this term is what causes the car detector with patches to go undetected. The MPS term encourages the colors of the patch to be as close as possible to the set of colors that can be reproduced by a printer, and the TV term encourages the patch to look smooth as well as prevent noisy looking patches to be generated. Essentially, both the MPS and TV terms help with the physical realizability of the patch. To generate physically realizable patches that can hide cars from being detected, we simply minimize this loss function using the atom optimizer. Here are some patches that were optimized on two scenes of attack. Type on are A0 size patches that are to be placed on the roof of cars. Type off patches are three rectangle shaped patches to be placed off and around the cars. GC plus W are patches optimized with geometric, color space, and weather transformations applied. And GC are patches optimized with only geometric and color space transformations applied. Before printing the patches off, we evaluated them on a test set of the two scenes. Here are some qualitative results of our patches in the car park scene. On the left are testing images with no patches applied. The left image is the original testing image and the right image is the weather augmented version of that testing image with snow applied. The middle images have patches with random pixel intensity values. These patches act as a control in our experiment. And the right images have our optimized patches applied. You can see that these patches are much more effective than the control patches. Our quantitative results also support this. Notice that patches optimized with only geometric and color space transformations were shown to be the most effective patches, which indicates the lack of value in performing weather transformations in the patch optimization process. Also notice that type off patches were found to be the most effective patch design in the side street scene. Now comes the most exciting part of this presentation, seeing how well these patches perform in the real world. On the right, you can see how the objectiveness score drops from 0.914 to 0.288 when the car is surrounded with our off-patch design in the side street scene. On the left, you can see a pair of cars in the car park scene with our patches placed on the roof, which also significantly reduces the objectiveness score. The table here shows the general efficacy of our physical patches, or the significant reduction in objectiveness score between 25 to 75%. You can see that we tested our patches in different real-world scenarios. For example, we placed the cars in direct sunlight or under the shade, as well as kept the car still or moving. Here, Type 1 patches were found to be the most effective patch design in both scenes of attack. The results also show that Type 1 patches are reasonably robust in different environmental conditions in the side street scene. In the car park scene, we can see the efficacy of the attack varies for the three different cars under attack. What we learned from this work is that while the efficacy of our attack is subject to environmental factors such as lighting, weather, and season, and the target observed distance, physical adversary attacks are a realistic threat to deep learning-based object detectors on aerial imagery. We hope that this work inspires some of you out there to develop new defense methods against these attacks.